Good morning, everyone, and congratulations for participating in an 8 o'clock class after a networking event last night. The session today is N87, the splice is right, and the PDH code is 72282. My name is Bob Barker. No, just kidding. But it's not far. I have a son whose name is Robert, and if Barker becomes Baker, my last name is Boulanger, which is baker in French, so not too far. So I'll start again. My name is Sylvie Boulanger. I'm with Supermetal, and we have a very special session today. I'll be moderating and speaking, and I'll be introducing our speakers. So the format is going to be a little different. It's called, I'm probably not going to pronounce this right, but a pichakcha? Somebody help me out? Okay, this is a kind of a session where the slides are pre-timed. So there's 5 speakers and we have about 10 minutes each, and each slide is 20-25 seconds. And once the speaker goes go, we don't touch the computer anymore, and we talk to the slides as they turn automatically. So we have a guaranteed timing, which is good for a lot of the speakers that are here. We're going to present different facets of the Splice. We're going to start with the design portion with Carol. I'll come in afterwards for the fabrication. Larry Kruth will, Carol Drucker, just said your first name, Carol Drucker. Then Larry Kruth will come in for the erection, Dwayne Miller for the bolted connections. No. I owed you one, I think. So just checking whether you're alert, and this is a pretty good test. So this for welded connections, and we'll have Terry Meyer talk about architecturally exposed structural steel. We left her at the end because she's got fantastic images. I think and she's a very courageous architect. She comes to our event regularly. So on that note, I will present each speaker. Carol Drucker is a principal of the firm Drucker Zidell Structural Engineers in Chicago. She's worked extensively on the structural design of many connection projects throughout the country and is recognized as an industry leader. She received her bachelor's degree in civil engineering at Purdue University and her master's degree in structural engineering from the University of California at Berkeley. She's authored articles on connection design and currently serves on the AISC's TC6 Connection Committee. Larry Kruth is consultant and recently retired vice president of Douglas Steel Fabricating Corporation and is also a member of their board of directors. With over 30 years of structural engineering experience, Larry is responsible for the coordination of all the activities of Douglas Steel. He's a registered professional in engineering in the states of Michigan and Pennsylvania. He's a member of the board of directors of AISC, chair of the AISC Safety Committee, and vice chair of AISC TC13 Quality Control and Assurance Specification Committee. He's a member of the AISC Research Committee, AISC TC6 Connection Design Specification Committee, AISC Full Specification Committee, and the Research Council on Structural Connections. Busy guy. He has been appointed to the MIOSHA Part 26 Structural Steel Erection Advisory Committee and MIOSHA Part 10 Lifting and Digging Advisory Committee. The Structural Engineers Association of Michigan has named Larry as the 2011 Structural Engineer of the Year. Dwayne Miller is Manager of Engineering Services for the Lincoln Electric Company. For more than 40 years, Dwayne has worked tirelessly to educate the world about structural steel welding. He's recognized as the top authority on the design of welded connections. He lectures and writes regularly for AWS and AISC, and 3 times has been awarded the Silver Quill Award by AWS for the excellence of his published work. In addition to frequent articles in modern steel construction, he is the author of AISC's design guide, Welded Connections. In 2011, he received the T.R. Higgins Lectureship Award, and in 2005, he received the AISC Lifetime Achievement Award. Currently, he serves as chair of the AWS D1 Structural Welding Code Committee and formerly chaired the Seismic Welding Subcommittee and the AASHTO AWS Bridge Welding Subcommittee. He's a member of the AISC Specifications Committee. And Dwayne is a very recent recipient of a most prestigious award, the Robert P. Stupp Award. Terry Meyer-Boak is our friendly architect. She is a full professor of the School of Architecture at the University of Waterloo in Canada. She's been teaching building construction, structures, environmental design, and film since 1986. She works with the Canadian Institute of Steel Construction, developing teaching resources for architectural education. She's the author of the CISE Guide for Specifying Architecturally Exposed Structural Steel. She's recently published 3 comprehensive books on steel and architecture for Berghauser: Understanding Steel Design, an Architectural Design Manual, Diagrid Structures, Systems, Connections, Details, and Architecturally Exposed Structural Steel Specifications, Connections, Details. Complex Steel Structures, Non-Orthogonal Geometries in Building with Steel is due to be published in 2017. She's an active board member of the Council on Tall Buildings and Urban Habitat, presently doing research on composite structural systems in tall buildings. Professor Boak is an avid photographer, now that's an understatement, documenting construction processes and completed buildings for her books, teaching presentations in various image databases. And this is something that's unique, the strong interest in not just the final product, but everything that goes into the building of it. And so she's not only helped architects, but she's also helped a lot of engineers. So on this note, Carol, would you like to come up?
Sure.
Sure.
All right, here we go. Can everyone hear okay? I think so. All right, well, thanks for coming. Friday morning, 8 o'clock. That's impressive, so thank you. I have a lot of content that I probably will not have time to cover, fortunately for you, due to time constraints. So if you would like a copy of this presentation, just email me, or better yet, follow DZSE on Twitter, and we'll be happy to send you a copy. All right, so do I just hit go, or what do I do?
Go. Yeah, just 0. Yeah, go.
All right, here goes nothing, right? All right, the good news is that the easiest type of splice to design is a typical gravity column splice. Minimal calculations are required, and the contractor, for the most part, should be allowed to go to AISC's manual, Part 14, and choose whatever type of gravity column splice they prefer to use for that project. Now, if you have an untypical gravity column splice, such as a built-up WT, then that is a different story. You need to check the splice for construction loading. Most likely, wind blowing on the upper shaft is going to control the design of the splice. We would still use an AISC splice as a minimum lower bound. To determine the wind load, ASC 705 can be used for ASD, or 710 can be used for LRFD, along with ASCE 37. ASCE 37 is good for loads on structures during construction, but because it includes the wind velocity reduction factor based on construction duration, and this you can use this to reduce the wind pressure blowing on the column. All right.
In advance, if you like.
Well, okay. Because if I say something, it's just going to go on. Typically, bolted column splices are preferred, but if for some reason you wanted to use a welded column splice, or you needed to, that certainly is included in the manual. Type 8 includes both a PJP and a CJP welded splice. Certainly, a PJP splice would be preferred over a CJP. And the PJP sizes in the manual are the exact same as the minimum PJP sizes given in the spec, based on material thickness. Now, if you have loading other than gravity loads, then for sure you're going to have to design your splice. You could have tension load due to integrity loading, especially in New York, or you could have tension due to lateral loads. Still, bolted connections are typically preferred over welded connections, but the very first thing to do when checking for tension in lateral column splices is to check if you even have tension. If you don't have tension, then you could use a typical gravity column splice from the manual. You can check load case by load case by load case, but if all that's available to you is an envelope solution, which is not all that uncommon, then make sure you use the minimum axial load with the maximum moment so you don't overestimate the maximum compression that's at the splice. The same thing for box columns, for built-up columns. Since the effective throat of the weld is typically small compared to the length, welds are commonly analyzed as having a length versus an area. Determine the appropriate section properties of your line weld. From that, you can determine your force per unit length, Once you know your force per unit length, you can divide by your available stress to get your required effective throat. In lieu of the elastic method of analysis, if you want to optimize your connection, reduce your number of bolts, or reduce the weld size, you can use more of a plastic stress block method of analysis, very similar to what we do in concrete, I hate to say it, or as what we do for base plate design in Design Guide number 1. Bill Thornton has a really good discussion about this in Tambouli's book. It's very in-depth. For seismic design, even columns that are not part, the gravity columns that are not part of the seismic force resisting system still participate in resisting the seismic forces. For that reason, the seismic provisions require the gravity columns to be designed for a shear force equal to the least plastic moment strength at the splice divided by the column height. Very similar requirement for ordinary brace frames, but for intermediate and for special concentric brace frames and BRBs, you have to design for a shear equal to the sum of the plastic moment strength at the column divided by the clear story height. And the flanges also have to be connected for the amplified loads or some minimum force criteria. For moment frames are very similar to braced frames, except for the flanges of special moment frames, intermediate frames, have to be CJP welded. In the new 2016 seismic provisions, PJP welds are going to be allowed with restrictions. Some would say with caution, or alternately, you can use a bolted flange splice, but it has to develop the expected moment strength at the splice. Okay, HSS splices are also included in the manual, welded column splices, but if you wanted to use a bolted column splice, just have to quit looking at Dwayne when I say that. We've used versions of all 3 of these bolted column splices on past projects. A butt plate splice is probably the most preferred cost-effective wise, but it's not always architecturally acceptable. You can use blind bolts or perhaps cut some access holes to access the bolts. It's always nice with trusses if they can be fabricated, shipped, and erected in one piece. But this is commonly not possible, and splices will be required. If you do need to splice a truss, it's good to coordinate that exact location with the engineer of record so you can get the appropriate forces in which to design the splices. All right. Well, if you're an EOR, I should say try to avoid full strength criteria. If you have a compression splice, it's really good one good alternative is to use end plates to transfer that compression load, but it's really not a free lunch because the AISC specification indicates for members other than columns, you have to design compression splices for stability force. That stability force is equal to 50% of the compression force acting in tension, or the shear and moment that results from 2% of the compression force acting in shear at the splice. Determine your shear force, apply it at the splice location, then you can determine your moment right at the splice. Use that stress block distribution, determine the tension in your bolts. Once you know the tension in your bolts, you can uncouple, you can design your bolts and then design your end plate thickness and the welds, very similar to Design Guide 4 for end plates. Here you see the top cord of a truss being lowered into place over the end plate splice. Just lower it down, bolt it up, works great. At the bottom cord, I don't know if you can see that, but bolted flange plates are used. You could use an end plate for a tension splice, but I would say that bolted flange plates are more commonly used. When designing bolted flange plates, you can use slip critical bolts and oversized holes, or if there is confidence in the fabricator and the truss is fit up in the shop, another good way to go is to use bearing bolts, N or X. You could reduce your bolt count by 50%, so it's really good. But also, if you have full strength, not necessarily even full strength splices, but for sure if you have full strength splices, it's good to lay out the connections and check for conflicts. You don't want to have adjacent connections hitting each other. Two common ways to analyze truss splices. Number one is you can just distribute the force according to area. In this case, your shear lag factor U is equal to 1 since each element at the splice is connected. Or alternately, you can just assign the whole entire tension load to the flanges and the web can be used to resist the shear. I guess you could also assign the whole tension load to the web if you wanted to. If you have a heavy splice, a good alternate is to put your bolts in double shear. We always draw these type of splices out in detail to check the bolt installation tolerances between the flanges. If you do have an issue, one alternate is you can use hex head bolts or threaded rods so the bolts can be both installed and tightened from outside the column. Oh, my timing's a bit off. If you are splicing a deep member to a shallow member, fills are going to be needed. One thing very, very nice about the 14th edition, probably the best thing about it, is the maximum reduction, bolt shear reduction factor for thick fills is now 15%. So no matter how thick your fill is, the maximum reduction is 15%. But for slip critical bolts, if you have multiple fills now, you have to reduce your slip resistance by 15%, so be careful with that. It's always good to order your material after the splice location is determined. In this top picture here, a shop splice was needed, CJP shop splice was needed in order to extend the member to facilitate a bolted splice in the field. Well, certainly in the shop, a PJP weld is preferred to minimize weld volume. If you can do it, do it. But in the field, I would say CJP welds are more common just due to fit-up tolerances and things like that. Now, both these splices are CJP welded splices. The first one is a tension splice, and the bottom is a full moment splice. In both these cases, the flanges resist the total axial load of the splice. It's kind of a no-no in today's world to share axial load between bolts and welds due to strain deformation compatibility. When checking that section of CJP welded truss splices, it's really good to remember the weld access holes. You don't want to get the shop drawings on your desk and realize a good portion of your web is missing and then have to reinforce the splice at that point in time. This is usually just an issue with tension splices, not compression splices. This truss, courtesy of AFCO steel, you can see daylight through those weld access holes, so they can get quite large. Now, splices are just not used for shipping and handling. They can also be used to optimize connection design. If you have members coming together at a joint and perhaps a bolted connection just is not feasible or a welded connection works better to transfer the load, you can weld the connection in the shop and provide a clean splice away from the joint in the field. All right, well, no time for questions, so.
Thank you very much. So just a couple of extra notes. We will reserve the questions at the end. We are going to go one after each other. And I forgot to present myself, a quick bio about my name. You know my name. And I'm Vice President Technical Marketing with Supermetal. And we have shops in Canada and the U.S. My main role is really, I work on special projects, especially in the early parts of multi-story buildings or bridge work. And I went to the University of Alberta for my undergraduate engineering, my master's at Berkeley, and I did a PhD in Switzerland. I used to work for the Canadian Institute of Steel Construction for many, many years. I write for Modern Steel Construction and Advantage Steel in Canada. I had a column called Ask Dr. Sylvie. That was a lot of fun. And I sit on the S16 committee, which is the Canadian Seismic Design Code. So you should note that we wrote an article together that was fun, wasn't it? In Modern Steel Construction in the March edition, The Splice is Right. And we proposed several tips to make sure that the splice is right. So Carol covered the first 4 tips, and I'm going to cover the next 3. Behind door number 1 is 8th Avenue Place, one of the projects I'll be covering that Supermetal did. Number 2 is Pembina Student Residence. Number 3 is an iron ore facility. Number 4 is an airport, the Calgary Airport. And number 5 is 707 5th, a 30-story building currently under construction by Supermetal. So I'll be using examples of splices from these projects. Tip number 5, the splice is right when a simple splice is introduced away from a complex joint. So you heard the design side, and we try as much as possible to put the welding in the shop where you can control it. And this is an example at the bottom where you have the stubs away from the column, which almost acts like it's like the tier becomes a bit of a tree. And the reason for that is you have a cantilever on the right-hand side of the column. If you see on the left, in the orange oval, you can see where this cantilever is happening. You can see also a diagonal which is holding the cantilever in place while the splice is being done. And afterwards, they go and remove those diagonals. You can see where it's positioned in the building. It's right at the curved area. And you notice there's no column. This is a real trend. Architects are just always removing corner columns, so always challenges there. Here we have a 200-foot span, a triangulated truss at the Calgary airport, and there's an intermediate support that's held up by 4 struts. You can see a better example on the bottom image. Now, because there's a high load coming from the span onto that strut, what they decided to do is do a solid square to transfer the loads. And what's elegant about this is because there's a pin there, there's a lot of things happening there. It avoided having a lot of extra plates and a lot of extra work. So that meant we had to have a shop splice away from that solid piece because you don't need it for the whole, and it would be really heavy. So the way the splice was done is you put plates inside the hollow section and you weld it in the shop. This is 8th Avenue Place. The Winter Garden is at the base of this beautiful building. And at the top, you have all these tubes coming into one area. So this is a complex node that you have to be able to address. The architects suggested one prototype, one alternative, and we proposed another to make our lives a little easier, but we had to make sure it looked nice because we knew we had no chance otherwise. Engineers can propose nice things too. So you see at the bottom, that's our prototype that we suggested that the architect approved. The top left side, you can see how we do this. So the advantage of this is while you're fitting up, you're really sliding a tube inside, so that gives us a lot of leeway. On the same project, we have a 2-story transfer truss. And in this example, the engineer gave us the load, but said, tell us how you want to build it, is pretty well how that happened. So because you have these heavy nodes, because there's two very tall columns, 50-story columns that are being transferred here, you have very complex nodes. So the idea is, as much as possible, we wanted to bolt on site and do all the complex welding. So where the complexity in this truss is all at the nodes. And that's where we concentrated our effort. And we made sure to try to respect Carol's approach that it's very important to have as much of a direct force transfer and make sure that the loads transfer as effectively as possible. And all you can see where all the welding was happening is really at the nodes. At the same time, we had to figure out how we were going to break this up. And you can see they were broken up around the nodes as much as possible in 3 elements. So 1, 2, 3. This was suggested by the fabricator, by us, in very good collaboration with the engineer. And the engineer then went and changed their IFC drawings. I'm continuing on the same project, but this time I'm going to talk about tip number 6. The splice is right when there is a trial fit-up of complex splices in the fabricator's shop or yard. So this is the 2-story building on its side. You can see the orange person in the middle there. That gives you a feeling of scale, so it kind of filled up our whole shop in reality. So what you wanted to do here is make sure that the 2 major splices worked. On the top right, you can see a tension splice. We use the splice plate as a template to put the holes in the shim plate. Then we use the shim plate as a template to put the holes inside the diagonal. It's like what's the story? I shouldn't be doing this. And you saw the really nice connection. There was a really, really strict requirement there that you'll see on video. So now we're at the Pembina residence. There are 4 full-story trusses per floor to carry the loads that go over an existing building. It's a 145-foot span, and there's 10 stories. So it's a very unique system. Each diagonal is actually a student residence. So there's a full truss that's split up in 3 for travel, but as you can see, the bottom cord is the top cord of the next truss. So what we had to do is really we shipped a cord with stubs away from it. Then we erected components with that way. So what was really important here is to make sure that it fit on site, as you can imagine, and that meant pre-assembly. So what we did is, you see the bottom part is the piece that's waiting to get shipped. So we never let that piece go until the top part fit properly. So we would fit the top part, we would bolt everything up. If everything fit, we unbolted, we put the bolts back onto the top part, and then we shipped the bottom part. So you can see there's a lot of complexity, and you can see the size of these on the right-hand side. Tip number 7, the splice is right when the location of the splice is optimized for handling. And that means manipulating, transporting, and erecting. So I'm kind of going a little bit in the erection side, but it's very difficult not to keep those separate. You'll see a little bit overlap between our presentation. So if you, on the left-hand side, you can see we had these big clamps that held up the three-dimensional truss in order to rotate it and put it in the proper position to weld it and to provide proper AESS welds and the like. We're up very high up north in Canada with an iron ore installation. This is a cantilevered truss you see on the right-hand side. Inside the orange, you can see 2 people, so you can get a feeling for scale for this. Now, when you go up there, there's hundreds of kilometers and it's dirt roads. So you really had to make sure that you optimize the transport. This is, I mean, our VP engineer is just incredible, Mark Robitaille, and this is his baby. And so the way this was done is frames. We used frames to be able to transport it. And look at the pink frame, we'll see it in the next slide, how the stubs stick out at the same time to facilitate erection. So these frames kind of, they're very neat because they kind of stagger. And at the end, we have frames that are like pointy and really fit together. So on the top left-hand side, even the cables were aligned so that one was longer than the other, so it already was lifted at an angle rather than going like this. So it fitted on the right-hand top image as a moment connection very nicely, and at the bottom you can see how you slide it underneath and it sticks out a little bit, and so on. Now we're at this is a building currently under construction. This is I didn't put Terry. This is one of Terry's photos. You can see that all the columns are at the same location. Unfortunately, that wasn't the case for all of the projects. So here what's important is to decide the splice location on the columns. And the splices are very complex. You can see on the right-hand side the complexity, which you see again here on the right-hand side. You have, these are 3 to 3.5 inch plates. It takes one guy to do a whole splice. It takes him a week. And so you have the web plates, and then, well, it's not just welding. I mean, it's heating up and warming, and then the final bolting of the plates and everything that goes into the splice. But it's a complex splice, as you can tell. So we initially received the splice location from the engineer on the left-hand side, and then we worked with the engineer to say, we have some suggestions to make. We don't make 5-story tall tiers, so we immediately cut those out. So you see on the right-hand side, we cut the tiers of the left portion. But on the right portion, something else is happening. We had big crane limitations, so we had to do several things. We had to reduce the weight, so it became 70 KSI, and we reduced the location of the splices. But what that meant is, as you can see here, that meant the splices got staggered. Not your ideal situation, so we had control levels. So at certain levels, we said, okay, we were back to having splices all at the same level and made sure that everything was lined up and coordinated, because of material availability was an important criteria. And sometimes it just gets complicated no matter what you do. This is a tension splice that's actually in our shop, and it's going to go at the bottom of a multi-story building in New York that's being performed by our friendly competitor, Walters. So in summary, it's important to try to simplify and get the stubs and get the complexity at the joint in the shop. It's important to trial fit in a lot of cases and be able to handle it. Thank you very much. Next.
Thanks, Sylvie. Just to give you a little background, Douglas Steel Fabricating is a structural steel fabricator and an erector, and we do about 85% of our own detailing in-house. So I was asked to join this group as an erector, and I'm sort of a blend of a lot of this stuff here, but I'm going to talk about this from an erection standpoint. I'm glad Sylvie brought up about staggered column splices on a job site. I didn't put that in mind, but I'm glad she covered that. When I'm talking about splices, I'm going to deal mainly with column splices, and I'm going to deal with the safety aspects, which are OSHA issues, and constructability. One of the questions we always get is, why do we always want a two-story column? What's the difference between a bolted, welded splice? What are the advantages of both? And there's other types of splices. Now, the photograph you see on the right-hand side, this was a 8-foot tall riveted column splice. We're not going to talk about anything like that. When we're dealing with OSHA, we're going to deal specifically with 1926 subpart R, the section of beams and columns, with column splices and perimeter columns. Both of these will come in play when you're dealing with safety for column splices on a job site. And as you can see, this was tip number 8 in the article that we were looking at in Modern Steel Construction. Specifically, 1926-756 states, each column splice shall be designed to resist a minimum eccentric gravity load of 300 pounds located 18 inches from the extreme outer face of the column shaft. Now, this part of the regulation was developed to account for a 200-pound iron worker with a 70-pound tool belt standing on a spud wrench at the top of the column, putting eccentric loads on the column. Also, when you're dealing with perimeter safety cables, it states in 1926-760 under fall protection that on multi-story structures, perimeter safety cables shall be installed at the final interior and exterior perimeters of the floors as soon as the metal decking has been installed. So this has to be accounted for, as you can see on the next slide, by paragraph E of perimeter columns. The perimeter column shall extend a minimum of 48 inches above the finished floor to permit installation of the perimeter safety cables. Following on in paragraph 2, it says that the perimeter column shall have holes or other devices attached to the perimeter columns 42 to 45 inches above the finished floor. That means there needs to be holes in the column to accept this perimeter cable. Now, what happens when you don't do that? If you put your column splice at mid-height, you have a picture like you see on the left. I have a person in a man lift trying to do a column splice. Or if you put it too close to the floor in a very inaccessible area, instead of accounting for it, you also have somebody in a man lift at a very low level, at the floor level, trying to complete the welding of that. These are some of the things that you should not be doing. They're actually in violation of OSHA. But if you look at OSHA, what OSHA was looking at when they thought of this rule was what you see on the left. You see the perimeter holes and the cables going through. But in reality, when you have a column splice at a perimeter, those column splice plates are right where the cable has to be for the top cable of the perimeter safety cable. So now you have to have holes in your splice plate. And many times the erectors will have those plates turned down. Now, if you run into a situation where this case, where they put the perimeter cable up, but they used holes in the web of the column just because of the way the column is located, and that's how they avoided the splice plate. You can see the splice plate where it's located. Now, there's a lower perimeter cable as well because there was multiple levels in this building, but this is how they got around that problem. Not always an optimal solution because you don't always have a situation where columns are located that way. What we do all the time is we locate our column splices 5 feet above the finished floor. By looking at 5 feet, looking at column splices there, the perimeter safety cables no longer interfere with your splice plates. And we have to remember, OSHA says 48 inches minimum. It doesn't say maximum. So you can move it to 5 feet. In my opinion, this is what OSHA should have done. That 48 should have been 60 inches. 60 inches is a very convenient height for an iron worker to be working at, to be able to work on a column splice, whether it's bolted or welded. So really, if I had been involved in writing subpart R, I would have suggested 60 for these reasons, but doesn't mean you can't do it. It's a minimum. So we get into constructability issues. Why two-story columns? Well, we're going to go back to that same issue. You know, column splice shall be designed to resist a minimum eccentric load of 300 pounds, 18 inches from the extreme outer face of the column. Well, that affects weak axis bending. Now, you may get an issue where you have a high load at the top, where an ironworker is standing on there, and you're standing at the weak axis. You're going to get some bending that's going to occur in your column. Here's an illustration of exaggerated of what you might be looking at. You see on the left a two-story column where the column's nice and stable, but once you get up 3 stories, especially on very light columns, stuff like you see on the right might begin to happen. Now keep in mind, obviously there are other loads other than this ironworker up there. You're going to have wind loads and other construction loads that are going to affect this to keep this thing stable. But you know, you need to take this into account. So if you have a normal column splice, a normal simple bolted gravity column splice, you're going to see something that is illustrated on the left, and you see the ironworkers very conveniently taking the upper shaft, putting it into position, putting the spud wrenches in, aligning things. This is the operation you can see. And obviously you see this is bolted. See the weather conditions in Michigan. It's not always the best weather conditions like you have here in Florida. So, but there are also some times when you may have to have a web plate for stability. You see on the left, you can see the column splice with the web plate. Now, the web plate's usually turned down. Sometimes the flange plates are turned down or spread out to enable the erection to take place. But even after this all gets together, you want to make sure that the splice is at a convenient height for the ironworker to be working at. You can see this picture here. You see how convenient it is. One of those rare nice days in Michigan when an iron worker is able to wander around and just tighten the bolts. You can see nice deck there, iron workers all in the area. Connection is very clean, very simple connection, and able to be reached very conveniently by keeping that column splice at a reasonable height for accessibility by the iron worker without having him to bend over or use any kind of equipment to get to it. Now, we run into situations many times where you're going to have an upper shaft smaller than a lower shaft. In this case, on the picture on the left, it's actually a much smaller column. And don't make your splice plates tapered. You can just move your gauge line and use the same plate in there. That works very well. The picture on the right just shows the fill plates being in place. This works very well as well from an erection standpoint, just to keep things together. Now, when you deal with welded column splices, what's very commonly seen is you have erection aids that are placed on the perimeter, like you see here, to help stabilize it. You have a web plate, and on the left is an illustration, on the right is an actual photograph of one. And you can see those big erection aids that are on there to facilitate erecting the column before the welding is taking place. Like I said, this is a very common way of doing it. Typically, what an iron worker will do once he gets the web plate attached, and once he will take off one of the erection aids to complete the welding. You can see the welding that took place on this one. A lot of weld has to go into place here. Granted, it's a very strong condition, but you have to remember weather conditions. You know, in your cold climates, you have to do a lot of preheat, as Sylvie was talking about. Preheat has to take place as well as the welding. It takes some time to get this done. One of the other simplifications that you can do, instead of using those very large erection aids, if you're not dealing with very much heavy loads, you can actually take 2 channels, put them on either side of the web. That gives you a lot of stability in both directions for a pre-attachment of your column splice, and you don't have those large erection aids in the way. Saves money for fabrication, saves time in the field from having to remove those. One thing you don't want to forget about is the splice between steel and concrete. You don't think about that as a splice. But every time you set a column down on a footing, that's a splice between steel and concrete. There's a lot of things to be thinking about that as well. You have the picture on the right, you can see you have the anchor rods in place, and you have to worry about situations with the anchor rods and worry about elevations as you're trying to make this work. You know, this is the typical thing everybody thinks about when you're looking at attaching a column to a base to a foundation. Yeah, very simply, very cleanly, the column goes down right over the anchor rods are always in the right place, sitting on the shim packs underneath, and these iron workers are great. They just everything goes perfectly and everything works perfect. Well, things don't always work out the same way, and you have to take things into account. Remember that 300 pounds, 18 inches off the column? Well, that affects that splice too. You're going to get an eccentric load on potentially on those anchor rods and in your base plate. There's a number of different things you have to think about. It's not just simply the gravity you think is going to be acting on that splice. There are other issues during construction that are going to affect that as well. In fact, if you look at AIC Design Guide 10, erection bracing, there are 3 specific items listed in that design guide. Bending failure of the base plate, buckling of the anchor rods, anchor rod pull-outs from the concrete pier or footing. Those are things you have to take into account when you're thinking about erecting these columns. So there's the eccentric load, the wind loads, also other construction loads being applied will affect it. Here are some examples of some problems you might run into. Now the one on the left is pretty typical. It's pull-out of anchor rods. If you look at the one on the right, that's a picture of a shim stacks with a broken off anchor rod. And on the bottom is a column sitting on shim stacks. Shim stacks create a problem. You know, them sitting there that way, an iron worker can kick those over as they're trying to set the column. Now you lost your elevation of the bottom of the base plate. What we do at Douglas Steel is we actually buy oversized washers and we drop them over top of the anchor rods. By dropping them over top of the anchor rods, they can't be kicked over. They're set to elevation. It eliminates a problem with the bending failure in the base plate, helps provide more stability for bending failure in the anchor rods, and the iron workers can't kick these over as they're setting the column. You always know where the elevation is. So in summary, things I want you to remember: column splicers are subject to eccentric loading during erection. Column splices must be 5 feet above the top of steel to accommodate perimeter cables. You restrict columns to no more than 2 stories due to weak axis bending. And remember weather conditions when specifying bolted or welded splices. And don't forget about the splice between the column and the concrete. Thank you.
Just a couple of notes before Dwayne comes on. There's a few people that came not exactly at 8 o'clock sharp, so I just want to give you the PDH code, which is 72282. And there are a lot of people standing at the back. There's lots of room at the front, so why don't you take, while Dwayne comes up, why don't you take some time and come and sit a little bit further front, if you want to. Okay. Dwayne?
Selvi, my time starts when I push this button,
yes,
right?
That's right.
Is this a wonderful session? And Selvi came up with it. Let's give her a round of applause. I think it's a super idea. A super idea. I am a little upset, however.
Uh-oh.
This is the kind of title that I should have for my session, and you came up with it instead. The splice is right. Well, now I just push this button and get started.
Yeah.
The splice is right when it's welded. Welds are obvious, welds are efficient, and welds are easy to design. And welds can be very economical. When we decide that we weld in the shop and bolt in the field, we lose the opportunity for some tremendous economic savings. We obviously have to do it right. We're talking about splices. A splice of a W14 by 730. This could be the tension cord on your truss. There's the bolted connection. Each connection has 6,900 extra pounds of steel in that connection. 128 high-strength bolts to make that work. And Carol talked about the problem of getting bolts inside that. You jump through a lot of hoops, but a welded connection is so simple. 70 pounds of weld metal does what 6,900 pounds of steel does in a bolted connection. Let's not lose sight of that. And when we went to contractors and asked for the difference in the price between the bolted connection and the welded connection, we had a reduction in cost of 79%. Now we have to do it right. There's a place for bolts. Frankly, I think they're screwy. But there's a place for welds. And we need to think through the economics of those connections. And if we're going to talk about aesthetics, I think one looks much better than the other. Carol, thank you for that beautiful picture of something horrible. All those bolts in there.
I think
The splice is, whose was that?
I have one of
What a beautiful, ugly picture. The splice is right when it is direct. When it's direct. Now, what do I mean by not direct? On the left, lap plates. These end plates. The splice is right when the splice becomes transparent. We're not talking about connections, we're talking about splices. And we kind of want that splice to disappear. And the best way to make it disappear is weld it. It looks natural. It looks logical. Sometimes our elements are not flat. We have rounded elements. We make structural steel look like a boiler house when we put those end plates in place, right? It's just, you just feel hot already when you see it. It's just crazy, all right? These knife plates, I think they are so ugly. A direct welded splice is so elegant, so beautiful, so efficient, and easy to do if we just decide to do it right. So the splice is right when it's direct. Now here are some examples where I think it's ugly. I'm supposed to be looking at the plants in the arboretum. I'm looking at these connections that look ugly. Oh, I understand. It's a little more than a splice here. It's part of the... That's the airport in Santiago, Chile. Something went wrong there on the right. I mean, we're just not thinking it through, right? And it just looks ugly. Now, in contrast to those, this is beautiful. That's Miami Airport. And the stained glass changes the color of the steel. Look, direct splices, beautiful connections that have satisfied the architectural concerns associated with this project. The splice is right when it's made direct. The splice is right when the welded connection details have been optimized. Now, we could talk about this for an entire session, and I have 20 seconds to talk about this kind of stuff. But I want to give you a few examples of where we optimize the details for the welded connections. Let's talk about splices on plate girders. In the top example, we like to get all the flange splices made first, all the web splices made first, then join those elements into the I-shaped cross-section. And those welds do not need to line up on the same plane. Now, years ago, we thought it was better to offset them, but we can put them on the same plane if we want to, but we don't have to. You get the splicing taken care of when you have simple plate elements and then join them into the more complex shape. Now, sometimes we need to take elements that are already built into I-shapes and splice those. When we do that, then we want to keep the splice on the same plane. And the weld access holes are stacked on top of each other. The groove welds are stacked on top of each other. It is acceptable to do what's shown in the bottom. There's no reason you can't cascade them, but it's certainly not a requirement. We can put them all on the same plane. The splice is right when field welded connections are given special attention. Now, my colleagues have been talking about weld in the shop and bolt in the field. They got it half right. You weld everywhere you can. But part of our problem is we don't pay enough attention to the details associated with welded connections in the field. And then because we don't pay attention to it, we have some disasters, and then we say no more field welding. Now, this is a stabbing point. This has been already discussed a little bit, where you can slide one tube on top of the other, and then the plug becomes a part of the backing. And that's a great way if you can assemble members that way. But we can't always do that, and particularly for field splices, we may not be able to utilize that concept. What if we have stubs on either end, columns, or we can't just drop that tube in there anymore? So now we have to think through that connection a little bit differently. And one way that you can do that is to miter cut or chamfer your intersecting members, and then you put in two split ring backers inside that. And now I can assemble it, my backing's in place. That can even be part of your field erection alignment system when we do that. So we need to think through the details of field welded connections with a little more finesse than maybe we would do in other situations. My final point, with the splice is right when welds are left in the as welded condition. I'm no fan of grinding off the reinforcement on welds. Usually a good power brush is adequate to get a good weld into a suitable condition, even for architecturally exposed steel, and I think we'll be on agreement on this one. Several pictures. On the left, the as welded condition. Power brush, painted, I think looks fine. On the right, a lousy grind. Didn't grind it all the way flush, it looks even worse than if you had left it unground. And that grinding operation is very expensive. And remember, we're getting strength out of these welds, and as we continue to grind and continue to blend, we start losing the reason we're putting in the weld. Now, I have a rough grind on the left, and I'm not sure the photograph shows it, but you know, it's not grinding. We end up polishing these welds. We end up polishing them to try to get the surface appearance. And then when you have a polished surface, it doesn't take the paint the same way the untreated steel does. And if you pay attention to these things, like I do, you'll see the difference. Thank you very much.
Before Terry comes on, I just want to, there's a disclaimer here on some of the things that Dwayne said about everything needs to be welded. I just wanted to put that in.
Well, good morning. This is going to be fun. I'm up last. So I'm talking about AESS because I'm the AESS woman for North America, I think, and the world. So the Splice is right when it's AESS. AESS is structural steel that's been left purposefully exposed. So it's not only the architecture of the space, but it's the structure of the space. And so it ends up requiring, more attention and more cost as a result. The Splice is right when it's designed for distance to view. This is the basis of everything we do in AESS, because if we look at a distance of, say, 20 feet, anything that's closer than 20 feet we can see up close, we need to fuss over. Things that are beyond 20 feet really don't require the same kind of attention to detail, particularly with splices. So this is a theater in England, and it's got all these sort of curved sections. But what you can see they've done, because we have distance to view, that some of the splices on those curved members look a little bit like the web reinforcing on those members, and so one blends with the other, and you can't really tell because of the distance to view. On this particular tree in the Reagan Airport in Washington, we have splices that are actually appearing in the middle. There's some very faint bolted connections. The rest of it is being shop welded, and so this has helped for the erection of these many trees in this very, very complex structure. The splice is right if you can make the splice inconspicuous. Splices are meant to be discrete. We don't usually celebrate splices. They're not connections. They're splices. And so it's really important that when we are aggregating very large members together on a site because of shipping constraints, that we have to make them appear unapparent. So we always have to consider the shipping size of an element. So this is part of a large structure that went in New York City, and this was the biggest piece that could fit on the truck. The whole structure is about 2.5 times this height, and so it had to be broken up into multiple parts. But it was really important for the entire integrity of the final piece that all of those be welded in the field beautifully. And so here you can see all of these tubes that are curved, they had to align all the curvatures. And so all of these, it was really, really important that this completely disappeared from view. And so the way that was handled in order to create these beautiful final structures required field welding of the highest order with complete grinding and remediation of all of those welds. Particularly important when you're using night lighting and uplighting, because that can accentuate any details that haven't been addressed on the site to an adequate level. And so this is the kind of work that you end up doing in the field in terms of not only applying all of the welds and the heating of the members, in this particularly in our cold climate, but also filling, yes, with body filler, sanding, and making everything look just, baby skin smooth prior to the application of the final coatings. And so we have to really consider, where is this important to do in AESS? Not everywhere, but but certainly in this little steel pedestrian bridge in Salt Lake City, because the size of those large curved members, that obviously had to be broken into smaller pieces to ship it, and to have had apparent welds would not have looked good at all. Likewise, for this truss, where we have about 150-foot triangular truss extending this way, and we have a curved piece that ends up becoming the column on the right, we needed to make sure that we had those unapparent, completely seamless welds on those cords, because it would have looked dastardly in AESS had that not been done. Now, on these tapered columns at the airport in Madrid, they've actually, Dwayne, left all of beautiful welds just exposed, but because of the color, because of the lighting, you can really hardly see those welds, and so therefore they're unapparent, even though they're as is, because of the distance factor. The splice is right if you consider using what we call hidden or discrete connections. The idea in AESS is to make the splice work with the overall idea of the structure as architecture as well. And so we are also looking for cost-saving ideas as a way to get to these kinds of splices. So you can consider the splice to be right if you consider using hidden connections. We have to connect, but we don't necessarily have to do it in a way that costs a lot of money. So what they're doing here with this particular splice is to use cover plates on the exterior that have to be, because it's an exterior situation, have to be sealed up in order to hide the bolts. This is the Calgary Airport, which was done by Sylvie's firm in terms of the fabrication and erection. So these super long trusses that she referenced in her presentation had to be spliced. Only the bottom cord is appearing below the ceiling, which is, of course, holding all the HVAC and the lighting. So on the top cord, that's her splice up there with the solid steel. These are actual pin connections, which are exposed, but they're up high. The bottom cord is what we were concerned about in terms of a hidden connection. So rather than doing that as a welded connection, it has cover plates. And the cover plates are covering a bolted connection, which happens quite quickly on the site. There's a lot of trusses, there's a lot of work going on, so that can be put together. The crane can be dismissed, and then this is all accessible by lift trucks in order to get up there to put those cover plates on. It's an interior condition, so then of course it doesn't also have to be concerned about weatherproofing. So once the plates are tack welded into place, then there can be filler put on that, and the thing can be sanded, and therefore the final finish is applied. And when you go to the airport and you're stressing about missing your flight, I don't really think you're going to look up there and go, wow, they didn't weld it. I don't know. So Splice is right if you consider using discrete connections. So these are what I call sort of combo architecturally designer connections. What you're trying to do is maintain the visual lines so that we don't end up with bulky plates, the butt plates, around the end that make it look like a boiler house, but you're trying to keep the lines there. So on this particular truss, they have used a welded connection on the top cord, which is curved, which might have called for it, but the bottom splice is done with plates that are actually sitting quite within the line of the truss. And so when you look at it in its final painted appearance as you're waiting for your taxi cab, I don't really think that those bolted connections, which could be more quickly done, would be a real big problem in terms of the final product on the site. That's at Baltimore Washington International Airport. Next time you're through, you might want to have a look and do a site inspection on that one. And this is the Seattle Public Library by Rem Koolhaas. It's a very energetic diagrid, and there's multiple levels of steel, so all the major pieces were shop fabricated, fully welded to the maximum size it could be transported. But because it's such a huge structure and there's so much of it, it was important to somehow cut some costs. It's a public library, of course, and so these are bolted connections that were done on site with extra welded pieces attached after they were erected for more stability. But these bolted connections fit really nicely, and you don't really notice them when you're there looking at the structure. Again, there's such texture to the structure. This is a transit station in Sydney, Australia at the Olympic Park, and again, because of the size of these huge curved trusses, they had to be transported in parts. and you'd have to look really hard to find the discrete connections along there, but it's broken into 3 pieces. You can see what these connections look like, and again, it allows for a fairly quick erection. There's a plate that's welded to the end of the tube. They subdivide the extension piece into chambers large enough for the bolting to take place, making sure there's enough for the wrench to go in there and as well to insert the bolt. And I think it actually makes a nice detail. A variation of this is used on a wind catcher in Masdar City. And again, what they're trying to do here is to keep the screen on the wind tower very tight to the structure, but they had to do some splices up at the top. And so what they're doing is a variation on the same kind of end connection detail, where here they have 2 bolts per chamber. They're using a cruciform welded extension onto the end of that tube. But what it does is create what we would call an architectural detail. And as I said in my talk yesterday, the way to speak to your architect is to say that this is a feature detail. It makes the structure more interesting, as opposed to we're doing this because we don't like welding. This is a very chaotic structure in Melbourne, Australia. It's called Federation Square. It's all finished in a galvanized corrosion protection system because they have a very corrosive environment, which is also being used as an architectural finish, and Sylvie loves when we use corrosion protection and an architectural finish. But here you can see that the welds, the Y-shaped welds, to create these larger aggregate elements in the shop, are done in the shop, and we've got some very tight plates that are sitting on the side of this that actually, from a textural point of view, are adding, in my opinion, to the look of the structure. And because it was such a chaotic structure, this allowed them to do it without a lot of extra welding on the site.
Thank you. We did it. Sorry, there's a lot of self-encouragement here for this kind of. We have time for questions. So please feel free to ask any one of us a question. No, you're not getting away with this that easily. I mean, we said a lot of things here. Surely, I mean, it's an 8 o'clock session, but still.
4 seconds per slide.
Yeah, that's right. Well, actually, I do have one, because I think what's happening is we're kind of sparking a debate between bolted and welded. Well, actually, for Dwayne, there's no debate, but I mean, for other people, there is. But it's interesting because I lived in Europe for several years, and welded connections on site is actually quite common. So when I came back and saw, just as soon as you talk about welded splice or welded connections on site, they go, ooh, you know. Mm-hmm. Well, Dwayne, I'm asking you the question. Why do you think that is?
I'm glad you asked that question. We talk about the proverbial chicken or the egg. We do so little field welding today, and that's not even been the case in the United States. 50 years ago, we field welded bridges. And our contractors had qualified craftsmen with experience with field welding. And we've deviated from that. So when we have a field welding project, we have rookies going out that don't have experience, and they botch it. And then for 5 more years, nobody uses it. And then we come up with field welding, and nobody has any experience, and they botch it. And then that kills it for another 5 years. And I firmly believe it is not technology, it's management, and it's experience. And you're absolutely right. In Europe, we do all kinds of things with field welding. And in these United States, we did field welding of bridges, cyclically loaded critical structures, and it works. So I think it's less technology, and it's more managerial oversight experience. And incidentally, you know, most of these bolted connections, to make them work, you have to weld, right? There's still welding. So I'm not, don't listen to this if you are employed by the Link Electric Company. I'm not really against bolts. I'm anti-concrete, okay? That's where we have some common thread here, all right? Most of your bolted connections need to have welding. All right, I understand that. The one thing I'm anti is just assuming that you can't field weld, because we can field weld. Yeah. And we can do very complex structures with field welding. We have to do it right. That's the challenge. We have to do it right. And I dare say that if we had the experience base that some of our European colleagues have, we'd have a totally different attitude about field welded connections, because the economy really is on the side of welding. Welding is such an efficient system. 70 pounds versus 6,900 is amazing.
Yeah, I noted that number, so I'm going to bring that one back.
But we have to do it right, and we have to have the experience. Thank you for the
Well,
question.
I'm going to add a comment to that, because in Europe, you have some of the fabricators' shop where the worker who's doing the welding in the shop is actually allowed to do the welding in the site, and I think that contributes to more welding in Europe. That's definitely a component. Yes?
Wayne, don't you feel that in the last 20, 25 years that and I'm not employed by political electors. Don't you think that the technology, this flux cord and so forth, has greatly improved the ability to both weld in the shop and in the field? I throw a softball at you.
And I appreciate it. Okay, so full disclosure here. The equipment, the technology is much better, and we have the ability to do a better job. Now, full disclosure, back when craftsmen or ironworkers learned to weld with stick electrode, it required greater skill. Welding with flux core doesn't require greater skill. Those skilled craftsmen that learned with stick did a great job with flux core. The newer generation that never learned on stick, learned on flux core, they don't have the high entry-level skills to break into the profession. And so I dare say that in some cases, the ease of the current technology has reduced the demand for the skills of the welder, and we probably all see that too. So it kind of cuts both ways, but the technology is so much better than we ever had in the past.
Okay. Question?
Just want to ask you this question. In my opinion, one of the problems we have with field welding right now is the workforce. And I just want to know, what do you think needs to be done to improve upon that? Because right now on a project like Falcons, my director is really concerned about field welding just because they are not feeling comfortable with the people they're hiring on the job, and they need hundreds of people on this job. So I have a feeling that the training that needs to be in place, somehow it's not in a bigger picture.
I'd like to first let Larry answer that question, because I think, I think that's relevant to the erection. Oh, the question was, it's the manpower of the people who field on site. There's a challenge there on getting the right people. So with respect to manpower, what can be done to improve the skill level of workers?
Okay, I'll try to answer that. You know, I understand your position, and it affects us not only in the field, but it affects us in our shop as well. The skill levels for welders in our shop as well. It affects us trying to find the people that are trained properly. I think one of the best ways you can do this is have great apprenticeship programs that really emphasize welding in the field. A lot of good. Stick from the union standpoint in this country, ironworker locals have great apprenticeship programs. Also, there are some non-union facilities that have great apprenticeship programs internally in their facility that do a great job of training people to weld. Unfortunately, there are many people that are erecting steel in the field that don't really understand the difference between welding in the shop and welding in the field. There's different conditions. There's different weld materials you use. You have weather conditions affecting your field. You have a lot wind conditions in the field. There's a lot of things taken into account. So to try to answer your question, more training needs to be done. I agree. There are some great training facilities out there, but are we as consumers willing to pay that extra cost to pay for that training for our employees? We have to realize we need to step up to that. We want to do quality work. We produce quality structural steel Facilities, we need to step up to make sure our employees are trained. And it's the responsibility of the employer to make sure their employees are trained.
Before I let Dwayne answer, we have a new welding training in our shop. It's called Women Welding and Wine, and it's a real hit. Dwayne?
Well, that's such it's a great question, and I think the answer is more complex. In my opinion, there's three ways wealth is generated: manufacturing, agriculture, and mining. Most everybody else just moves money around, right? The investment bankers, the lawyers, the doctors. I'm not saying they don't do a good service, but they're just moving money around. Manufacturing, agriculture, mining create wealth. We take things with less value and add value. But those industries are under attack. And I don't think manufacturing's valued, not like it was 50 years ago. And blue-collar work, I mean, to be a craftsman was an honor in the past. And to learn a skilled trade was an honor. And frankly, I guess it's my generation that we told our kids, you have to go to college, get a degree in something really stupid, take out $100,000 worth of loans so that you can work at McDonald's. That's nuts. We need to elevate the importance of manufacturing in the United States. That's where we create wealth. And we have to elevate the stature of crafts jobs, skilled crafts jobs. And we at Lincoln are working very hard at we work with the skilled unions and training programs, our virtual reality to train new welders, drawing young people in who learn video games. It's natural to go to to our Vertex virtual welding system. And so we're drawing people. We have a trailer that goes around to state fairs with all the Vertex virtual reality sponsored with Lincoln and the American Welding Society to try to draw people in. We're losing welders faster than we're replacing them in our industry. Now, just so you know, we haven't given up at Lincoln. That's why we're investing in automation, because we think we probably will never repopulate our people, so we're going to automate. And that's how we're going to be competitive in a world economy where people are willing to work for a lot less money than what we want to work with in the United States. So it's a big challenge. It's a big challenge. We need to hit it on multiple fronts.
Okay, that was quite a complete, and we had a bit of philosophy in there as well.
Can I add one more thing?
You can have one more round, Larry.
Okay, this is going to be very short. One thing we do at Douglas Steel is every few years, every 2-3 years, I take everybody from our engineering department and we go to the local community college in Lansing and we have them try to weld. I want everybody who's drawing a weld on a drawing to understand how difficult this really is. It's not just drawing a little bevel on there and drawing this little weld symbol and it all goes away. It's a lot more difficult than that. It helps tremendously when you're dealing with that training on that end on what ends up on the other end.
Sure. And for having experienced the welding very recently, I've been involved so many years, but I did I mean, the women welding and wine, we really did it. But just doing the welding, when I went back to our shop, all the welds looked beautiful, you know, because...
It was the wine.
The wine came after, by the way. Yes, okay. So there are questions. Can we maybe switch topics a little bit if you have a question? So we have three, so I'll come here.
So Larry, back to your, you mentioned several times about the OSHA rule for the 300-pound eccentric load rule. And I think if any engineer applies any wind load at all to a freestanding column, they'll find that overturned moment from the wind load is several times higher than that OSHA rule. So I consider that particular rule the most dangerous OSHA rule that exists.
Did everybody hear the question, the comment? Yes? Okay.
Well,
Larry,
the question was concerning the 300-pound OSHA rule that I quoted, and the question dealt with the fact that wind loading on that column during erection will far exceed that 300-pound eccentric load. And that's something to be aware of, because don't just take the OSHA rule, take the wind loading into account. I did mention, after being criticized by one of our co-panel members here, that I forgot to mention wind loading, so I mentioned wind loading in my presentation. I'm giving a presentation later on this afternoon where I will show you how to take care of that wind loading. So be around. So be aware of that this afternoon. So I agree wholeheartedly. Wind loading can do dramatic things to your structure that a lot of people don't even realize takes place.
Okay, good answer. Over there, the back, and then I'll come back to Robert Shaw.
Lest Dwayne get too big ahead on the recent award, here's a little thinking about field welding. Number one is inspection. Usually there's a UT requirement which keeps you from putting the deck on, which keeps the concrete operation from happening, and if there is a problem, you end up digging for it. So it's an unknown, it's a wild card. To paint, of course. The ironworkers sometimes spend their time removing paint. 3, in a place like New York City, you have an operating engineer for every 2 welding machines, and usually a fire watch. 4 is the preheat. It's an unknown, another wild card. You never know when the schedule's actually going to hit, and that can be a considerable amount of time. And finally, rod ovens. Not everything's done with wire feed. You need a rod oven on each floor, practically speaking, when you're doing the welding. So, and there's more, but it should be approached with caution, because it's not just about beauty or ease. There are other unknowns that come into play there.
Was that it? I mean, do you have another point?
That's all we're down to now.
No. So those are very good observations. Would some of the panel members like to comment? We're good? Well, thank you.
Well, I will. So, Saul's my friend, okay? You ought to see what my enemies do to me. I agree with everything he said. You see, I'll repeat, the only thing I'm anti is the conclusion, weld in the shop, bolt in the field. I'm okay with coming to a rational conclusion of bolting in the field. If it's a rational conclusion, you've thought it through. Just give me a shot. Just give me a shot. That's all I'm asking. If I lose, I lose, okay? But we come to the wrong conclusion when we shut the door to good alternatives. That's my message.
Okay.
So we take all those things into consideration.
Right. Thank you, Dwayne. There was a question, yes?
Yeah.
Sorry.
When do we start, when do we have to stop welding because of weather? I mean, if you have 3-inch plates and you have 20-degree minus, can you weld? Can you preheat? Is it forbidden? I mean, cost-wise, would it be prohibitive, expensive to preheat if you?
So, I'm not sure everybody understood the question. Would you like to repeat
All right,
it?
I'll repeat the question. I think it's at what temperature do we stop field welding because of the cold, okay? The one thing to remember is preheat is the welder's friend when it's cold, right? And they always like to preheat in the wintertime. So Mr. Shaw is going to correct me because he's really good at details. I think we say down to 0, right, don't we, Bob, for the welder, or is it minus 20?
You mean that 2-hour discussion we had in committee on Friday?
Yeah, that's right.
Fahrenheit or Celsius? Fahrenheit, but what's no longer in.
Fahrenheit or?
Oh, we're doing Fahrenheit. We're in the U.S., right? Okay. The D1.1 code says that, let's go through it, 2 or 3 things. If it says no preheat and we drop between under 32, no preheat, if you're under 32, you have to preheat to 70 regardless. All right, so if our normal conditions, no preheat, and we drop below 32, you have to preheat to 70. Then, if we get below 0 degrees, we stop welding, and it is for the welder's comfort that we do that. It's not the steel. The steel that's properly preheated can be welded at lower temperatures. You're going to have to keep adding a lot of energy in there, but welder comfort becomes a problem, and so we cut it off at 0 degrees. F, 0 degrees F.
Okay. And
I didn't get Cindy's permission before I brought this question up. There are some new Group C bolts in the new AIM specification that could reduce the size of some of those massive bolted connections. Take 1,600 pounds of connection material down to, say, 5,000 pounds, and from 128 volts to, say, 90 volts. And that might make them look better and smaller, more compact, and more economical. That's all I'm going to say.
Okay, so this is a marketing, this is a sales pitch?
So the question is, I agree with that, do I? So, hey, consider.
No, I'm not, I'm not going to, we've had experience, but I'm not going to share it. So, next question?
I'm not against fuel welding either, but we do a lot of work in Manhattan, and it is very expensive to fuel weld in Manhattan, and nobody wants to do it on purpose. One of the things, my observations is that in New York especially, everybody's in love with slip critical bolts, and I'd like to know what happened to X bolts.
So, who would be able to, do you want to answer that? Yeah.
I know, I got really lucky. Well,
Yeah.
I just asked one of our clients in Chicago who's an erector, when do you prefer to use X bolts over slip critical bolts? And he said, if he trusts his, basically, I don't know if I should say this, but if he trusts his fabricator, he wants to use N bolts, or X bolts, even better yet. I think in New York, at least from our experience, X bolts are kind of, it's a hard sell on the East Coast. In the Midwest, we use them all the time. You can check the thickness of the ply closest to the nut and see if you have an X bolt condition. Larry Muir and Bill Thornton put it in one of their PowerPoint presentations, and they have a really nice convenient chart, or you can calculate. I think the 3rd edition manual had a little table in there, so you can visually just check it. You don't have to get out there and measure. You can check it. But I think it's erector preference really based on confidence with their fabricator. It depends how sophisticated the fabricator is.
Did you want to add a comment, Larry?
Yeah.
Yeah, I'm going to try to answer that a little differently. You know, as for what you're asking about the difference between slip critical and X bolts or N bolts, if you actually read RCSC very carefully, it's a very limited range you need to use slip critical bolts. Very, very limited. So I guess to try to answer a question, adding to what Carol said, I personally don't prefer to use X bolts in the field. As good as ironworkers are, I get very concerned that what's in my bolt bag goes in the connection and not the bolt that I'm supposed to put in there. So I get very, very concerned. And it's very convenient. I mean, you think if you're way up in the air and you're stuffing bolts, and all of a sudden this one needs to be a 1/4 inch or 1/2 inch longer. This one fits, works, the nut's flush, it'll still work. And they walk away from it. So it has to be carefully inspected when you're trying to specify X bolts. We always do try to stick with N bolts as much as possible. If you're going to use X bolts, I always make sure that it's a big cloud on the erection diagram and it's marked very boldly, and we have our field inspector, our personal field inspector, make sure those are what are used in the connection. So I try to avoid X bolts at all possible. In the shop, I don't have a problem. I have good control in the shop. But when you're up in the air, things like that happen all the time.
Okay, but sometimes what we do when we're using X bolts is we'll make sure to ask the detailer to put a note on the erection drawings to make sure that the nut goes on the detail material side, if it matters. And if it doesn't matter which side the nut goes on, and then I think a lot of connection engineers would use them if it's okay with the engineering record and the...
Okay, I think there was, I saw another hand there trying to keep the order.
We're using X-type bolts when we know that any outer plies are thick enough that you're sure to begin with that you're going to be in the...
Right. If you have a 1-inch ply in a 3/4 inch bolt, you're going to have an X bolt condition.
That's right.
You will. Whether you count on it or not, you're going to have it. And if you have 2 1-inch plates, for sure you're going to have an X bolt. So it's a 25% increase in strength. So $25, you're going to lean over and pick it up.
Okay, and I know there was a question on this side. No questions?
There's one in the back.
Oh, in the back, sorry, that's it, the back, yes.
Carol, on the design engineering side, you typically see your people specify, CJPs is the easy answer. How do we convince you guys to put on your drawing effort into defining your loads, and specifically column splice. That's the easy one. Percent retention, CJP is the easy way to go. Then you got RFI and national loads, and then it's a fight to get the envelope loads just to try and design a simplified connection. Now, how do we get your side to kind of put that little bit of extra effort in and help us out on that side?
Well, that's a really good question. All right, so when we do connection design, the question is how do we get EORs to stop doing CJP welds, mainly on column splice designs, right? Because it really is, they know it's okay. They don't have to take the time to design it. You can just weld it up and you know it's going to work. Well, when we do connection design for fabrication, if we dare show a CJP weld, we know we're going to get a phone call. So we avoid that like the plague because we know it's coming. So no CJP welds if we can avoid it at any cost. But on the EOR side, we do a little bit of EOR work, and I think I don't think we would do it, but other EORs would do it. And in lieu of that, you can simply put the forces on the drawings and have the contractor be responsible for connection design. I think if you do see a project where the column splice welds are CJP welded, you can ask for the forces so you can optimize them. But sometimes you have to pay the EOR, which I can't get that through my mind. You have to pay the EOR to have the luxury to design your column splices. So I think if you're an EOR and you're listening, please do not charge extra to give information that should be supplied as part of your contract, in my opinion. But I know it's a tough thing, and sometimes there's a comfort feeling with engineer of records that they just want that extra robustness in the lateral column splices, and I guess I can kind of understand that one from the design side, but technically, you should design for the forces, especially if there's no tension in your column splice.
Okay, good. I have a question for Terry. Because of the work we've done together on AESS, I found that architects really like welded connections, like at all costs. But there's in your presentation, there's sort of sometimes there are compromises on bolted connection. What is in the architecture community? How would you say that? You find a balance between, sort of a nice-looking bolted connection and the preference, the high preference towards welded connections?
Well, I would say that a lot of it has to do with the overall aesthetics of the structure itself. And so most larger sort of agglomerated structures tend to be smoother in terms of their design. And so that would tend towards welded connections to do that. I would say that most architects are not particularly well educated in structures. And so when they don't draw the connections. They don't think about the connections. They draw things that are all continuous. And so it takes a bit of doing, and that's why a lot of the architects that are involved in some of the projects I showed are very high-end architects who are noted for designing in steel because they've taken the time to understand and make the steel connection design sort of a signature part of their architecture, and they choose certain connection styles for different projects. So that when you get into very high-end architects, I think they understand that, or the ones that are good at steel design. And when you get sort of the middle of the road, they don't understand it at all. AESS or otherwise, I mean, particularly since AESS is really only picked up steam in the last 10, 20 years. And so they're coming from a generation of architectural education and mindset that says the structure is covered by drywall. What do I care? The engineer can do whatever they want. The fabricator, it's just not my business. Make sure the building stands up. And so there's a big shift with AESS for architects to have to understand how that goes together. And even though I teach that at the university level, you are still, really pushing on students to design the connections, to take that as part of their piece. And it's just so much easier. I mean, that's why, I just always, I love dynamic reinforced concrete. I'll tell you, the works of Saarinen and Pierluigi Nervi and those kind of guys, wow, that's beautiful stuff. But slab high-rise condos is just the most boring material, ever invented, although functional. And what it allows when architects design in concrete, they translate that into their designs in steel. They design the exterior of something and they don't own what's inside. And so therefore, they design steel as if it was concrete, as if it was all welded, because then they don't have to think about the connections.
Okay. So on that note, and it'll be 9:30 in 30 seconds, so you get a 30-second break. Excuse me, the PDH code again is 72282, is 72282. Thank you very much for coming.